Here is the count of prime numbers, drawn as a staircase. Every time you pass a prime, 2, then 3, then 5, then 7, the line steps up by 1, and between primes it runs flat. Up close, the steps look haphazard. Sometimes 2 primes sit just 2 apart, and the stairs jump quickly. Sometimes you climb a long flat landing with no prime at all. But now zoom out, all the way out to 1,000,000, and something quiet happens. The jagged little staircase, seen from far enough away, hugs a single smooth curve almost perfectly. By the time you reach 1,000,000, the exact prime count is 78,498, and that smooth curve predicts 78,628. The two agree to better than 2 parts in 1,000. The roughness never disappears, but it rides along a clean, simple shape. So a real question almost asks itself. The smooth curve and the true count are close, but they are not the same. There is a gap between them, a wobble, and the wobble is exactly the part that looks random. How big can that gap get? Is the staircase chained tightly to the curve forever, or could it wander far away out where no one has counted? That single question, how far the primes can stray from their smooth prediction, turns out to be worth a great deal. A man named Bernhard Riemann, writing in 1859, found where the answer is hidden. The strange part is that he found it hiding somewhere that has at first glance nothing to do with prime numbers at all. The somewhere is a single infinite sum. Take every whole number, 1, 2, 3, and onward, raise each to some power and add up the reciprocals. With the power set to 2, you are adding 1 plus 1/4 plus 1/9 plus 1/16, and the total settles down to about 1.645. Pick a different power and you get a different total. As long as the power is bigger than 1, the sum always settles on a finite number. Now here is the move that makes this worth caring about. That same sum can be rewritten as a product, with one factor for each prime and nothing but primes. 1 over 1 minus a half to the power, times 1 over 1 minus a third to the power, times 1 over a fifth, a seventh, and so on through every prime. Multiply those prime factors together and you land on the exact same number as the sum over all the whole numbers. Leonhard Euler proved this equality holds, and it is genuinely strange the first time you see it. A sum that ranges over everything equals a product that ranges over only the primes. The reason behind that equality is just unique factorization wearing a disguise. The plain fact that every number breaks into primes in exactly one way. So this sum is not really a statement about all numbers. It is a statement about primes, repackaged. Whatever this function knows, it knows about the primes, which is the first hint that it might know about our wobble too. The function has a name, of course. Written with the Greek letter zeta, it is the Riemann zeta function, and for now it lives only where that power is bigger than 1, because that is the only place the sum makes sense. There is a wall here, and we need to get past it. The sum only adds up to something finite when the power is bigger than 1. Set the power to 1 and you get 1 plus a half plus a third plus a quarter forever, which grows without bound. So as written, the function simply does not exist to the left of that wall. Half the world is blank. But there is a standard tool for exactly this, and it is one of the quietly miraculous facts of mathematics. If a function is smooth in the strong sense that complex numbers allow, then the piece of it you can see determines the whole thing uniquely. There is one and only one way to extend it past the wall while keeping it smooth, and that extension is forced. You do not get to choose it. The values to the left were, in a sense, already decided by the values to the right. We let the power become a complex number, a point in a plane rather than on a line, and the function spreads out to fill almost the entire plane. The single exception is that one point, at the power equal to 1, where it shoots off to infinity and genuinely cannot be patched. And the instant the function reaches this new territory, it starts doing something it never could before. It hits 0. Out in the freshly filled region, there are inputs where the zeta function equals exactly nothing, and those zeros were invisible from the half of the map where we started. They only exist because the function was extended. Keep your eye on those zeros. Everything from here is about where they sit. The zeros come in two families, and telling them apart is the whole game. The first family is tidy and completely understood. At the power equal to -2, the zeta function is 0. At -4, 0 again. At -6, -8, every negative even number marching off to the left, the function is exactly 0. These are spaced evenly, they are easy to prove, and frankly nobody loses sleep over them. They are called the trivial zeros, and the name is honest, because once you know the machinery, they really are routine. The second family is where the trouble lives. Every other zero of the function sits inside a vertical band, the slab of the plane where the real part of the power is between 0 and 1. This band has a name, the critical strip. The zeros inside it are called the non-trivial zeros, and unlike their tidy cousins, these are the ones tangled up with the primes. We can compute them. The first one sits at real part 1/2 with an imaginary height of about 14.13. The next at about 21.02, then 25.01, then 30.42, then 32.94, climbing up the strip. Look closely at those first 5 though, because something is staring at us. Their heights are all different. 14, 21, 25, and so on, scattered with no obvious rhythm. But their left to right position is not scattered at all. Every single one of them has real part exactly 1/2. They are not spread across the strip. They are threaded onto one vertical line straight up its middle. That line down the center of the strip at real part 1/2 is called the critical line. And the pattern we just noticed is the entire million-dollar question. So let me state it as plainly as it deserves. Bernhard Riemann, in that 1859 paper, conjectured that this is no accident. His hypothesis is that every last non-trivial zero, all infinitely many of them, lies exactly on that center line. Not most of them, not the first few billion. Every one forever pinned to real part 1/2. That is the Riemann hypothesis, stated in a single breath, and I want to be completely honest with you about its status. It is a conjecture, it is not a theorem. In more than a century and a half, with the full weight of modern mathematics thrown at it, no one has proved that the zeros must lie on the line, and no one has found even a single zero that strays off it. It sits exactly between proved and disproved, which is the most uncomfortable place a statement can sit. Now, some of this is solid ground, and it is worth separating what we know from what we hope. It is a proven theorem that infinitely many of the zeros do lie on the line. It is proven that all of them lie strictly inside the strip, none on the very edges. What is open, the one missing piece, is whether the strip might hide a stray zero somewhere off the center, even slightly off. A single zero with real part not equal to 1/2 would destroy the hypothesis instantly. The whole towering question is whether that one renegade exists. So far, everywhere anyone has looked, it does not. Let me show you the zeros directly, because they are not abstract. You can watch the function hit them. Walk straight up that center line, holding the real part fixed at 1/2 and letting the height climb, and measure the size of the zeta function as you go. Plot that size against the height. The curve starts up around 1.5, dips and rises, and then at a height of about 14.13, it plunges all the way down and kisses 0. That touch is the first non-trivial zero. Keep walking and it happens again at 21.02, again at 25.01, again and again the curve diving to the floor at each of those exact heights and nowhere in between. These heights are not guesses or pictures, they are computed to enormous precision. The first one is 14.134725, and it is known to far more digits than that. People have calculated these zeros by the billions and then by the trillions, and we will come back to just how many in a moment. Every one of them that anyone has ever pinned down has landed with its real part sitting on 1/2, the curve touching 0 right on the center line, exactly as Riemann guessed and no one can yet prove. Here is the payoff. The reason a question about a function's zeros is really a question about prime numbers. Remember the wobble, the gap between the true prime staircase and its smooth curve. Riemann found an exact formula for it. The size of that wobble, the error in the prime count, is controlled directly by the zeros. Each zero contributes its own ripple to the gap, and the position of the zero sets how loud its ripple is. A zero sitting far to the right in the strip would pump a large, growing error into the prime count. A zero sitting on the center line contributes only a small, controlled one. So the location of the zeros and the wildness of the primes are the same fact told two ways. And this is what turns the hypothesis into something worth a fortune. If every zero really does sit on the center line, then every ripple is the quiet, controlled kind, and the prime count is locked as tightly to its smooth curve as it could possibly be. The precise statement is that the error stays within roughly the square root of the number times its logarithm, and you cannot do any better than that. Primes would then be, in a strict and provable sense, as well behaved as they are allowed to be. The Riemann hypothesis is exactly equivalent to that tightest possible bound on how far the primes wander. Proving the zeros are on the line would prove the primes never stray far. They are one statement, so how much evidence is there really for a thing nobody has proved? An enormous amount, and that is part of what makes it maddening. More than 10 trillion non-trivial zeros have been computed. 10 to the 13th power, every one checked, and every single one of them lies precisely on the critical line, real part 1/2, with no exception ever found. If this were a question settled by evidence, it would have been settled long ago, overwhelmingly. But a hypothesis about all infinitely many zeros is not the kind of thing checking can finish. You could verify the first 100 trillion, and the very next one could betray you, and no amount of counting rules that out. Proof is a different currency from evidence, and here the two have come completely apart. Which is why, in the year 2000, the Clay Mathematics Institute named the Riemann Hypothesis one of 7 problems and attached a prize of $1 million to each. The money is real, and it is still sitting there, unclaimed for this one. But anyone who works on it will tell you the million is not the point. The point is that an astonishing amount of modern number theory has been built on top of this conjecture, with theorems that begin, in effect, with the words, if the Riemann hypothesis is true. A proof would convert a vast hanging structure of maybe into a structure of certainly, all at once. That is the real prize. So that is the whole shape of it. The primes look ragged, but their count hugs a smooth curve, and the gap between them is governed by the zeros of one function. Those zeros, every one we have ever found, sit on a single line down the middle of the strip. Riemann guessed that they all do, that the primes are as orderly as they could possibly be, and a century and a half later, that guess is still standing, still unproven, still unbroken. It is worth holding the two halves of this side by side, because they really are both true at once. On the one hand, we know a great deal. We know the zeros exist, we know infinitely many of them are on the line, we know exactly what their being on the line would mean for the primes, and we have checked more than 10 trillion cases without a single miss. On the other hand, the central claim that not one zero anywhere strays off that center line has never been proved and might be hard beyond anything we currently know how to do. Knowing that much, and still not knowing the one thing, is a very particular kind of frustration, and also a very particular kind of invitation. If there is one thing to carry away, it is that the apparent randomness of the primes is not really randomness. It is the music of a set of zeros we can see, almost all of whose secrets we understand, hiding one secret we cannot yet reach. That last secret has a price of $1 million on it, and it has outlasted every person who has chased it so far. This was one more in a series on hard questions and the people who chased them. Stay for the rest.